For problem 5, we will have insulating spherical shell. Insulating spherical shell with inner radius A and outer radius B. This is insulating material. For part A, we will have charge Q uniformly spread over the volume. Charge Q uniformly spread over the volume. And for part B, we will be given charge density, charge per unit volume. Charge density or charge per unit volume. Let me just write charge density. Rho, where rho is charge per unit volume, it will be C, where C is a constant, and R, where R is in radial distance, in radial direction. So C is a constant, and charge density does not depend on angle. For both cases, we need to find the electric field everywhere. Find the electric field everywhere. We will use Gauss's law to find the electric field everywhere. And Gauss's law states that integral flux of electric field E dot ds through the closed surface is equal to the charge enclosed by this surface divided by epsilon naught. S stays for the area, surface area. This is Gauss's law, and now we need to write the definition of charge per unit volume. So rho is charge per unit volume, per unit volume. By definition of rho, dq, infinitesimal charge, is equal to rho dV, where V is infinitesimal volume. Then, if charge is uniformly distributed and rho is constant, so for part A, we will have uniform distribution of charge. Uniform distribution of charge. Then what do we have? So now we start working with part A. If I have uniform distribution, rho constant, then what is rho? Rho is just charge divided by volume. For part A, rho will be charge divided by the volume of this spherical shell, which is 4/3 pi b cubed, and I need to subtract this whole, which it has volume 4/3 pi a cubed. So we know charge per unit volume, this is rho, and now I'm ready to apply Gauss's law to find the electric field everywhere for part A. So the first region that we will consider will be R less than A. I will put 1. R less than A. My Gaussian surface will be imaginary sphere with radius R, that is arbitrary R, that is less than A. I use symmetry. Electric field is in the same direction as ds. There is spherical symmetry, so I take E out of this integral. Integral ds is integral of sphere 4 pi r squared. And this is equal to the charge enclosed. Charge enclosed is 0. For r less than A, electric field is 0. Now we move to R between A and B. R between A and B. And I will probably move this solution right here for you to be able to see it better. So for R greater than A and less than B, we will consider Gaussian surface within this insulating material between A and B. This is my Gaussian surface now. The left-hand side will be the same. I have E times 4 pi r squared. The left-hand side. The right-hand side is 1 over epsilon naught times Q enclosed. Charge enclosed by Gaussian surface is charge within this volume. So we need to find out what is the charge between little r, sphere of little r, and A. Let's do it. So I have 1 over epsilon naught. Charge enclosed is rho, which is Q divided by 4/3 pi B cubed minus 4/3 pi A cubed. This is rho, charge per unit volume, times volume. So rho, one more time, is charge divided by volume, and now Q is rho times volume. So what is the volume enclosed by this Gaussian surface of arbitrary radius r? Volume is 4/3 pi r cubed, and I need to subtract this whole because it is a spherical shell, minus 4/3 pi A cubed. Rho times volume enclosed by Gaussian surface. So now I'm ready to find the electric field. So what is the electric field? Electric field is now, let me do it in green. It is, let's simplify here a little bit. So it is 4/3 pi, 4/3 pi will cancel out, and I will erase rho to have more space. So I have 1 over 4 pi come here, 4 pi epsilon naught. Then I have Q right here. And then I have r cubed minus A cubed divided by B cubed minus A cubed. And we don't forget this r squared. So it is Q over r squared. This is the expression for the electric field between A and B. We need direction because of spherical symmetry. The direction is radially out. Now we need to find the electric field for R greater than B. So the last region where we are looking for the electric field will be R greater than B. My Gaussian surface will be outside of this spherical shell. It's arbitrary sphere with radius, arbitrary radius r that is greater than B. So now I need to write Gauss's law for this region. Left-hand side is unchanged, so it is E times 4 pi r squared is equal to 1 over epsilon naught, charge enclosed by this surface. What is charge enclosed? It is rho. This is rho. What is Q enclosed? It is charge enclosed by this surface, and charge enclosed by this surface is just total charge Q that was smeared of this volume. So I put charge Q. And then the electric field E is 1 over 4 pi epsilon naught Q over R squared, and the direction is radially out. So we found the electric field everywhere, and from outside, the electric field created by this uniformly charged insulating sphere look exactly the same as a point charge that I put at the center. So I will write the answer that I raised for R less than A. Electric field was 0 because the charge enclosed was 0. For R between A and B, this is the electric field that we found. And for R greater than B, this is the electric field. So we are done with part A for uniform distribution of charge within this insulating spherical shell. For part B, charge is not given. Instead, charge density, charge per unit volume is given. Rho is equal to given constant C times R. I need to find the electric field everywhere, and again we will be using Gauss's law. Integral E dot ds is equal to charge enclosed divided by epsilon naught. For R less than A, we will consider this Gaussian surface. We have spherical symmetry, so I have a sphere with R less than A. Left hand side will be E times 4 pi R squared. Charge enclosed is 0, so electric field is 0. Now, for R greater than A and less than B, this will be our Gaussian surface, imaginary Gaussian sphere located within this insulating spherical shell. The left-hand side will be the same, E times 4 pi R squared. The right-hand side will be 1 over epsilon naught, charge enclosed. So let's write again definition of rho dq is rho dv, then q is integral rho dv, and I need to integrate this over the volume. So what is dv for the sphere? Infinitesimal volume is 4 pi r squared area and then dr. This is infinitesimal volume. And then I need to bring it here. I need to write q enclosed, which is integral rho, where rho is provided, it is CR, rho dv, and dv is 4 pi r squared dr. The limits are from A to arbitrary r, where arbitrary r is radius of Gaussian surface. So I integrate from A to r. Let's take this integral. I have 1 over epsilon naught. C is constant, 4 pi constant. So all is left. I have r cubed dr from A to r. And then I have 4 pi C over epsilon naught, r to the 4th over 4 from A to r. And when I plug in the limits, we will get 4 pi c over epsilon naught. 4 and 4 cancel out. And then I have r to the 4th minus a to the 4th. Now we are ready to find the electric field in this region. So I have left hand side E times 4 pi r squared I divide the right hand side by this 4 pi r squared. Pi and pi will cancel out. So we have c divided by epsilon naught. And then 4 right here. This 4 is still here. And then I have r to the 4th minus a to the 4th divided by r squared. And we do not forget the direction. The direction is radially out. We found the electric field between A and B. Now we have the third region left. The third region is R greater than B. For R greater than B, I have this Gaussian surface. This is my R, arbitrary R. And I use Gauss's law. Left hand side is the same, E times 4 pi r squared. Now the right hand side of Gauss's law is 1 over epsilon naught. And then I have integral of rho dv, no changes here. Q is rho dv, rho is CR, dv is 4 pi r squared dr. What are the limits of integration? The limits of integration, what we are looking for charge enclosed by this Gaussian surface. But where is this charge? This charge is right here between A and B. There is no charge at any point greater than B. So total charge enclosed by this Gaussian surface is just total charge in this spherical shell. I need to integrate where the charge is, and the charge is between A and B. So my lower limit is A, my upper limit is B, and what I'm finding right now, this integral, is the total charge of this spherical shell. So I have 1 over epsilon naught, then I have 4 pi c, 4 pi c, r squared r gives me r cubed dr. When I take this integral, it will be r to the 4th over 4, and the limits are from A to B. So now I will write my final answer for this region right here. So we are moving here. I will erase Gauss's law and we will erase definition of rho. We already used it. We will erase dv. So when I plug in the limits, 4 and 4 cancel out. So I have pi c over epsilon naught, pi c over epsilon naught. Then it is b to the 4th minus a to the 4th. And now we are ready to find the electric field. I have E times 4 pi r squared on the left. I divide right hand side by 4 pi r squared. Pi and pi will be gone, so we'll have c over 4 epsilon naught. B to the 4th minus a to the 4th divided by r squared, and the direction is radially out. I remind you that this region was R greater than B, so we found the electric field everywhere for this distribution of charge. Charge per unit volume was given. We found the electric field for R less than A. We found the electric field for R greater than B, greater than A and less than B. So our electric field for this region is right here. And we found the electric field for R greater than B. Problem solved.